Having covered the basics of oscillations and introduced the central theory of simple harmonic motion, we now look at a more realistic setting where we have damped oscillations. So when we think of damped oscillations, we're thinking of more realistic systems where energy is dissipated to the surroundings. This is a process that we call damping. In the most common case, the damping force is proportional to the velocity of the mass that's oscillating. So it opposes the velocity, and in a similar kind of structure that we had to the acceleration, the damping force is proportional to the velocity. So it's negative, so it always works against the velocity. What this means is that when we observe the amplitude of the oscillations over time, we see that the amplitude, or the energy stored in the system, decreases by a constant percentage in each cycle, with an exponential decrease. So we see the blue line here showing the decreasing amplitude of the oscillation, and the shape of the decrease is described by that exponential decay in orange. So, as an exercise for damped oscillations, what we'd like you to do to think about a mass on a horizontal spring experiencing a drag force of minus BV. So what we'd like you to do is show that the equation of motion is described in this form. Pause the video and we'll come back to the discussion afterwards. So in this case, we're looking for a solution in the form of this differential equation. So mass times the acceleration plus b times the velocity plus k times displacement. Is that equal to 0? Well, let's look at the net restoring force on the mass oscillating. So the mass is moving to the right with velocity v. We expect it to, because it's got a positive displacement, we would have a negative accelerating force back towards the equilibrium and also a negative drag force on the velocity as well. So the net restoring force F is the sum of these two forces, which we can write as a form of a differential equation, minus kx minus b dx by dt. We then use Newton's second law to put this together. We say the mass times the acceleration is equal to the restoring force. And we can see that if we quickly rearrange that, we end up with the same equation at the top, the same form of the differential equation. This is the equation for damped simple harmonic motion. It describes how the damping behaves, where the damping is proportional to the velocity. We can model a damped oscillation in a fairly straightforward manner. We assume that the amplitude decays exponentially with timescale 2 tau. The reason for using 2 tau will become apparent later on in the course. The damped oscillation frequency omega prime, it may vary from the natural frequency of the undamped oscillator. So if we were to superimpose the undamped oscillator on this, we might see that the period is slightly different, the angular frequency being slightly different as well, due to that damping process. The solution, therefore, takes the term of a double exponential. So we have the original amplitude, A0, we have our decay of the amplitude, the e to the minus t over 2 tau, and then we have the oscillation itself. So what we've done here is we've described two components. We have the oscillation in blue, and we have the decay of the amplitude, or also known as the envelope, which contains that oscillation decaying with this orange exponential here. We can show that this is indeed a solution by differentiating it and substituting it into the equation of motion we uncovered before. So we'll leave this as an exercise for you to do. This substitution will work when we have an expression for tau, which is equal to m over b, and we have an expression for omega prime squared. The square of the angular frequency of the damped oscillation is a modified version of the undamped angular frequency with this term b over 2m as a modifier. And it's possible to determine these factors from the differentiation. So make sure that you're able to follow through that derivation. The general solution of damped oscillation comes in two forms. We have our complex, as we described earlier, and we have its trigonometric form as well. In this case, A0 is the initial or the maximum amplitude, and tau is the characteristic decay constant. We've already said that we can determine it from the solving differential equations. And we also have an expression for omega prime related to the frequency of the undamped oscillator. And remember that for a mass on a spring, we can calculate omega 0 from the spring constant and the mass that's oscillating. Okay, let's have a look at an exercise. What does the damped SHM solution look like when b is 0 and when b is equal to 2m omega 0? Pause the video and use these equations to examine what the damped solution might look like. Well, let's look at a situation where b equals 0. So b equals 0, we plug this into our various equations. We find that the exponent, the envelope describing the decay of the amplitude, goes to 1. So this term, the exponent goes to 1. and we find that the angular frequency of the damped oscillation, because this term goes to 0, is simply equal to the original undamped frequency. So we have an expression for x is a to 0 e to the I omega 0 t plus delta, which is the expression for an undamped oscillator. So this is undamped SHM. If B is 0, we have no damping, we have undamped SHM. What about when B is equal to 2m omega 0? Again, we put the values in. If we say that B is equal to 2m omega 0, we get omega prime is 0. And that means what we end up with is a non-oscillating system. There is no period of oscillation. There is no angular frequency. So the system is damped to such an extent it doesn't oscillate. There are a number of factors to think about in damped oscillations. What happens when we increase the damping factor B? As we increase it, we see that omega prime decreases. So if we look here, as B increases, omega prime decreases. We get slower oscillations, lower frequency oscillations. Tau, this characteristic damping period, decreases, so the amplitude decays more and more rapidly. Any further increase of B over and above the 2m omega 0 leads to the system not oscillating at all. So let's look at what happens when we increase that damping factor to an extreme extent. When B is equal to 2m omega 0, we have that critical damping situation where there is no oscillation happening. That's this blue line here, where the system returns as quickly as possible to its equilibrium position. It returns to that equilibrium position in its shortest time. If B increases above this point, we have overdamping, where B is considerably greater than that critical damping constant, and the system very slowly returns to equilibrium. We can think of it in terms of a real-world analogy, where critical damping is, imagine pushing a child on a swing, is when you apply exactly the right amount of energy to quickly return the child to the 0 point, but not allow them to swing back and forward any further. Whereas when we think of overdamping, you could almost imagine putting a spring oscillator into treacle, where the treacle just allows the spring very slowly to come back to its equilibrium position, but it doesn't allow any level of oscillation to happen, and it doesn't allow the system to move freely. So, in summary, with damped SHM, the damping force is proportional and opposite to the velocity, and the frequency is generally lower than the undamped oscillator. We see it in this graph here. We see that the dotted black term, where we have slight damping, has a very slightly longer frequency than the undamped oscillator in grey. The amplitude itself decays exponentially. We saw that before. We have that description of an envelope which contains the oscillation. We'll use that envelope term numerous times throughout the course, and you'll see it in signal processing and so on. When we have light damping, we see oscillations with decaying amplitude, that exponential decay. When we have critical damping, we have the fastest possible decay to the 0 point, but there is no oscillation which takes place. And we have overdamping, where there's much slower decay and absolutely no oscillation, so the system returns very, very slowly back to its equilibrium point.